Hi and welcome back again. Consider the following optimization problem. You plan to have a party at your local park, but since you expect some rainy weather, you want to place a party tent. There's a nice elliptically shaped grassy field where you could place this tent. You can see the equation describing the shape of the field on the screen, where x and y are measured in decameters. Since you want none of your guests to get wet, you want the tent to be as large as possible. However, in order not to hinder the other visitors of the park, you are not allowed to place the tent on the surrounding path. Of course, in order to maximize the area, you need to place the corners of the tent on the edge of the field. So we let the point x, y denote one of the corners of the tent. Since we want to maximize the area of the tent, this means that we want to maximize the function 4xy. However, we should not simply try to maximize the function 4xy by itself, since there are restrictions on the values of x and y that are allowed. Indeed, the point x, y lies on the edge of the field, so it satisfies the equation x squared plus 4y squared equals 16. We call this restriction a constraint on the optimization problem, which means that we only consider those values of x and y that satisfy the constraint. So summarizing, we reformulated the problem to that we want to find the maximum of the function 4xy subject to the constraint x squared plus 4y squared is 16. So how would you find the optimal value to such a problem? We will come back to this example at the end of the video. Let's first have a look at optimization problems more generally. Finding optimal values is a typical problem in engineering. Usually, we formulate them as that we want to find the maximal or minimum value of a function q under some constraints. Typical examples of these constraints are that all input values should be positive, or that the input values should satisfy a system of linear equations. Constraints can also be that the input vector should be of unit length, and we can also want the input vector to be orthogonal to a given vector. These constraints are often necessary in practice because of technical or physical limitations. In this video, we focus on the case where the function q is a quadratic form, and on the third and fourth type of constraints. Let's start with an example of an optimization problem that involves the third type of constraint. Suppose we want to find the maximal and minimal values of the quadratic form 2x1 squared plus 5x2 squared subject to the constraint that the length of the input vector should be 1. This constraint means that we restrict the graph of the function to the blue line and try to find the maximal and minimal values on this part of the graph only. In this case, a simple estimate will do the trick, so there's no need for linear algebra here. We can estimate the quadratic form by noting that 2x1 squared is always less than or equal to 5x1 squared, and taking the 5 out of the brackets allows us to plug in the constraint directly. So we find that 5 is, at least, an upper bound to this optimization problem. But is it also the maximum? Luckily, we can easily see that the q of the vector 0, 1 is precisely 5. So 5 is indeed the maximal value. For the minimal value, we can perform a similar computation and we obtain that the minimal value is 2. However, here we were just lucky that we can easily bound the quadratic form. What could we do, for example, when we want to optimize the quadratic form 8x1x2 plus x3 squared, subject to the constraint that the norm of the input vector should be 1? This problem cannot be solved using simple estimates only, so we need a more powerful tool here. This is where linear algebra comes in. The following theorem tells us what to do. We let A be a symmetric n by n matrix with eigenvalues lambda 1 up to lambda n, which are ordered from large to small, and eigenvalues with a higher multiplicity are listed several times according to this multiplicity. Then the maximal value of the corresponding quadratic form under the constraint that the norm of x is 1 is equal to lambda 1, the largest eigenvalue. This value is attained if x is any unit eigenvector corresponding to this eigenvalue lambda 1. Similarly, the minimal value of this problem is lambda n, the smallest eigenvalue, and it is attained if x is a corresponding unit eigenvector. We will not prove this result here. Let's instead consider the example we could not solve previously. The corresponding symmetric matrix has eigenvalues 4, 1 and -4, with corresponding eigenvectors v1, v2 and v3. According to the theorem, the maximal value is the largest eigenvalue, which is 4, and is attained for the unit eigenvector v1, while the minimal value is the smallest eigenvalue, which is -4, and it is attained for the unit eigenvector v3. But what would happen if we add another constraint, that the input vector x should be orthogonal to the first eigenvector v1? Since this matrix is symmetric, its eigenvalues are orthogonal, so the eigenvector v3 satisfies this additional constraint. Since adding a constraint can never make the minimal value smaller, -4 remains the minimal value, as it is still attained at the vector v3. However, v1 is not orthogonal to itself, so we do not immediately know what the new maximal value is. In this case, we can write out what it means to be orthogonal to v1, and we can plug this relation into the quadratic form. In this restricted quadratic form, we can easily read off that it is maximally 1, when the input vector is the second eigenvector 0, 0, 1. So why would you want to consider this type of extra constraint? Well, such an orthogonality condition plays an important role when considering the so-called singular value decomposition of matrices. So if you study this decomposition, you will definitely encounter this type of constraint. Now, how would you solve such a problem in general? For that, we have the following theorem. Suppose we are in the situation from the previous theorem, so the eigenvalues λ1 up to λn are ordered from the largest to the smallest. We let u1 up to un be a corresponding orthonormal set of eigenvectors. Then, the maximal value of the quadratic form, subject to the constraint that the normal vector should be 1, and that x is orthogonal to the first k-1 eigenvectors, is equal to the next eigenvalue λk. This maximal value is, at least, attained at the eigenvector uk or -uk, but it might also be attained at other vectors. Of course, the minimal value remains the same, as the final eigenvector satisfies all additional constraints. Please note that the theorem only works for the constraint that x should be orthogonal to one or several eigenvectors. General orthogonality conditions are much harder to deal with, and we will not delve into these optimization problems here. Let's now return to the optimization problem from the start of this video. Using new coordinates, we can reformulate the problem as that we want to determine the maximum of the quadratic form 32x1, x2, subject to the constraint that the length of x should be 1. The corresponding symmetric matrix has eigenvalues plus or minus 16. So according to the theorem, the maximal value is the largest eigenvalue, which is 16. And it is attained at the corresponding eigenvector 1 over square root of 2, 1 over square root of 2. Of course, this is also the maximal value of the original problem. So the original problem is solved optimally when x is 4 over the square root of 2 and y is 2 over the square root of 2. And the corresponding area equals 16. That's it for now. Don't forget to practice the material and see you next time.